correlation. Correlation is basically doing nothing else but telling you there is an association, and it gives you a direction in which this association points. So it's warmer, you sweat more. This is not a good example, but it's like you get the idea, right? It's like it's positive. Something is higher, the corresponding associating variable is also going to be higher. Then you have the inverse, which is an inverse correlation, where basically something is higher, the other variable decreases over the range of data. So that's correlation. And the continuation of correlation is the so-called regression. In regression, you're basically utilizing the principle of a correlational analysis to predict a dependent variable based on the independent variable. So you're basically utilizing this association to predict an outcome or a dependent variable. So a determination of a correlation is correlational correlation. It's the first step, and the second step is the prediction, which is basically a regression. So for today, we're sticking with correlation only. We're going to do a little example today. What's important to keep in mind with correlation is that correlation, just because something correlates, that doesn't by no means mean that they're causally related. What does that mean? If I correlate the temperature in New York City with the water level in Venice, there may be a correlation for whatever reason, but it's not causally related to, well, given climate change, it may be correlated for some causal reason, but essentially it's not directly associated. So it doesn't mean that there's causality involved. So this is important, and Norton and Heinzen outlined this here, that correlation is not causation. Particularly when you look at large data sets, you're very likely to find a correlation which may not be true. And we spoke about spurious correlations. Spurious correlations is, for example, the association between, drowning deaths and ice cream consumption, which was just something that may be affected by a third variable, but it's basically not a real association. What's very characteristic for this kind of analysis is that both variables need to be scale variables. So both the dependent and the independent variable are either interval or ratio variables. That means they change in the same direction. If you don't really have in a correlation, you don't really have a dependent or independent. You have the dependent only by hypothesis, meaning if something is an outcome, you will determine it still with the independent variable. So if you think that people eat more ice cream because whatever event is happening in their life or whatever event, if it's warmer, it's more ice cream. So then you would consider the dependent variable, the outcome variable, which is the ice cream consumption, and the independent variable would be on the x-axis, and that would be the temperature, the ambient temperature. So, and they're pointing either in the same direction or not in the same direction. And this is what we're showing here. Not here, but on the next one. The quantification of this correlation is then done with the so-called correlation coefficient. So this correlation coefficient can be either positive or negative, depending on the direction this association presents. So if it is a warmer temperature, more ice cream, it's a positive correlation. So the correlation coefficient will be positive too. And in its most extreme way, in its most extreme form, it will be at +1. That is like a perfect correlation. If somebody shows you an analysis with a +1 correlation, that individual is lying, and you will need to ask for the data. I have seen that once in my review career, and that was the only time I wrote back to the editorial office, like, I'm not gonna even look at this without seeing the data myself. So it's virtually impossible to find a correlation coefficient of 1 in a real data set. If you have 2 points and you connect them, then yes, then it's 1. If you have a negative correlation, it's -1. So the strength of the correlation, forgetting about the direction of the association, is the absolute value of this correlation coefficient. If you're interested in the direction, the smaller the inverse correlation, the stronger the association. The more positive the positive correlation, the stronger the association. So the strength is really quantified by the coefficient independent of its sign. So smaller, closer to -1 indicates a stronger correlation. So it's really that absolute number that indicates a strength. And here we have positive correlations, and this is that example where you go with the research question. So the dependent variable here is vocabulary size at age 2, whereas the independent variable, bless you, is the number of different words the infants have heard during the time of their 2 years. Bless you. So you basically make sense, and likely there's a causal relationship, right? But you can, even with something that is as intuitive as this, you cannot establish causality. Of note, the only time you could establish causality using a retrospective analysis like that is by replicating it, determining genetic or biological association. So there are 11 criteria by a former, I think it was a CDC director in the 60s or 70s, named Bradford Hill. So he determined the 11 Hill criteria that allow for establishing some form of causality in retrospective analysis. But that's epidemiology that may come later at you. If not, then forget about it. Keep it in mind. Keep it in mind. But basically, even this is not establishing causality. But there is an understandable association that if kids, infants, hear a lot of words, they're more likely to have a better vocabulary at the age of 2. Logically, right? So this is a positive direct relationship. That's a positive correlation. A negative correlation is an association which basically shows a decrease in the dependent variable with an increase of the independent variable. So the example here is the final exam grade in a standardized fashion is going to be smaller with a higher proportion of homework copied. Which is also an understandable association, which kind of makes sense also in causal terms, but again, we cannot establish causality. So one thing that you may note is this line that goes through this scatter. So this, we remember, this is a scatter plot. And a scatter plot, you can quantify the direction by fitting a line through it. And we talked about this. This is the line of best fit, right? And the line of best fit, and this is now where we're coming back to your high school knowledge. The line, if you have a linear equation, you have a y, which is the y-axis, equals a slope multiplied by an x plus an intercept. And we're getting to that at the end of this class and the next during next class. This basically will then allow us to develop a so-called regression equation, which is nothing else but a linear equation. We're going to play around a little bit with calculating slopes, and finding the intercept is also quite simple. So any questions on that? What's always important to note is that this little diamond-shaped shape that indicates this one point here, that is one way how to indicate outliers that have a lot of weight. So obviously the line of best fit and your correlation is going to be affected by outliers, and therefore they need to be kept in mind. We're not going to talk much about outliers, but just as a quick heads up, you may be tempted, if you do analysis down the road by writing your master's thesis or whatsoever, you may be tempted to kick those outliers out and just like, okay, let's not talk about them anymore, let's just delete them. This is a big no-no, and you should not do that. So there's outlier exclusion is a science by its own right. So that needs to be properly justified if you exclude these outliers. So in the same context, you have a perfect positive correlation, which is, as said, most likely inexistent and most likely not true. There's something wrong with the data that you're being presented for. You will not see that in real life. Just when you think about it, exam grade versus number of absences, you will not find such a line when you have 7 data points. It's quite unlikely. So that's a perfect positive correlation or a perfect negative correlation, equally implausible. When you quantify this correlation coefficient, so you have from 0 to -1 or from 0 to +1. 0 to +1 or greater than 0, 2 + 1 is a positive correlation, and the stronger, the larger that number. Smaller than 0 up to -1 is a negative inverse correlation. Basically, the smaller the number or the larger the absolute value, the stronger the association or correlation. The conventions here are small correlations are 0.1 to 0.3, medium 0.3 to 0.5, large 0.5 and above. So that's not $1 million question. So you have what is larger, a correlation of 0.25 or -0.74. And I hope that's not a question for anybody. Which one is larger? No, the absolute value. It's the -0.74. It's because it's larger in an absolute magnitude of that number. So it's either more negative for negative correlation or more positive for positive correlations. Misleading. Didn't speak about that ice cream example before? No. Okay. So these are those spurious correlations. So let's assume somebody quantifies the ice cream consumption on a beach and then the number of drowning deaths and finds a correlation of 0.91 between those two variables. So now the question is, which one is the dependent variable? So is it that people drown more because they eat more ice, or is it because they eat more ice because they drown more? Hard to say, because other people around them drown more. It's kind of hard to say, but basically it's a spurious correlation because it has nothing to do with the causal factor associating with either ice cream consumption or drown deaths. So the logic, does anybody have an idea why that? Yeah.
Because of summer.
Yeah, exactly. So it's just more likely that people eat ice cream, and obviously that's when people go into the pool, into the ocean, into the lake, or whatever surface water you basically want to soak in. So that is a correlation that essentially is it's a mediated correlation. It's actually not a spurious correlation; it's a mediated correlation. And this is essentially where we're going next. So you have invisible third variables, and this is where the whole conversation gets a little bit complicated, because just because A correlates with B and B correlates with A, that doesn't mean they're causally related. There may be a third factor in between, which is C, which correlates with both. And that actually is the causal factor. So it's beyond the scope of this class to discuss this in much detail, but basically in epidemiology, where you have like multifactorial associations that you try to quantify all of them and get a handle on all this association, this becomes a science project, because you're mapping out these associations in something that is called a directed acyclic graph. And that's basically mapping out, and there's software to do that. Actually, I can show you that. And there's software to do that. the software to do this properly. It's called Dagity. And Dagity, basically, you can utilize Dagity to basically build these associations and export them then. So these associations, like if you want to quantify, so D is now ice cream deaths, B is not ice cream deaths. Drowning deaths, B is, no, it would actually be different. So that's drowning deaths. No, ice cream consumption as the outcome. This is drowning deaths is not correlated, but that would be temperature. That would be drowning deaths essentially. So you have basically you mapping out the associations and in which direction you think the associations are pointing and why. And then you basically use sophisticated algorithms to essentially figure out how strong are the associations, and you try to kind of split down these associations into the respective pathways. So how much weight is on that pathway as compared to how much weight is on that pathway. And to some extent, we're going to get into this when we talk about regression, but basically you can use this with multivariable analyses. But again, beyond the scope of this class. But this is basically, this is the power of third variables. So you have invisible third variables, and the true problem is that in many cases, you don't have C. Nobody told you what C is. And if you have an idea what C could be, maybe it can't be measured. Classical problem is like all kinds of lifestyle factors, right? In our outcome analysis, what we are facing, it's like you want to quantify a cardiac event, somebody having a heart attack, and you want to quantify this in a population. So A, you don't know who of these people in your population are smokers, and if they're smokers and they have reported that they're smokers, they're for sure not going to tell you how much they're really smoking. That's for sure. That's if you get an estimate, those of you who go into medicine, somebody tells you they're a smoker. First of all, you got to be lucky to tell you, even honestly, they're smokers. If they're telling you, yeah, I smoke like 5 cigarettes, it's like multiplied by 4 at the very least. So nobody is honest about his or her bad habits, and as a consequence to that, you don't quantify these third variables. And that's not only true with lifestyle, obviously. There are many examples of that, particularly when it's large populations. You just don't quantify every variable. You don't know what's really happening, and you're tapping in the dark, trying to identify factors that actually leading for you to see an association that you see quite solidly and robust in your data. So go back to the correlation coefficient. Okay, so first of all, we're only dealing with linear relationships. So no, bless you, no nonlinear relationships. So that's a science by its own right. So it's a linear relationship, and the correlation coefficient, the Pearson correlation coefficient, is quantifying the linear relation between two scale variables, either interval or ratio. So it's a linear relationship. It's symbolized with the italic letter R when it is a statistic based on sample data. So it's the same story. Remember, like the M and the S, there was sample statistic, and then you have sigma and mu for mean and standard deviation in the population. Same concept applies here. R is for sample statistics. So this is when you do correlational analysis on a sample, then you're looking at an R. And if you're doing analysis on a population level, then you quantify your correlation with a so-called rho. Rho is basically this turned around 9, and it's the Greek letter R for R. So, so now you're going to ask us a population health study. When do I see population health studies? You will see quite a lot of population health studies when you read, for example, reports from the WHO. Or you remember that analysis we saw from the happiness reports, the bubble graph, chapter 4, the visual displays. We had different countries. and there were, what was it? Like the size was the size of the country and the color was the happiness. And they all were like, I forget what the graph was labeled, but basically it determined socioeconomic factors and happiness. So if you take such a graph with different population depicted and you fit one trend line through and you say there's an association in my population study, then you would refer to this as a row. If you're basically studying the association between ice cream consumption and the ambient temperature in a group of 20 students, that's your sample. Then you're quantifying an R. Good. Any questions? I think correlation is considerably intuitive and it's a fun topic actually. Up until now. Now it stops being fun. So that's the equation used for quantifying the correlation coefficient. It's not a terrible formula. It looks a little bit more intimidating than it actually is. So what you essentially do, so let's just look at the big picture. You have a numerator and you have a denominator. The numerator, so forget the denominator. The numerator is basically the sum of the product of those differences. So we're quantifying the mean of X. That's everything, and the mean of the independent variable. And we're subtracting that mean from each individual entry of X. Then we have a Y. That's our dependent variable. We're quantifying the mean of Y. We're subtracting that mean from each individual Y. And by that, we get those deviations, right? We're multiplying then these deviations from X and Y. And we're summing all these products up. That's our numerator. So obviously, if, and now try to kind of follow along a bit what I'm saying. If you have an my, and an mx, and you have now a tendency that this goes rather to the positive, that means the mean is small, the mean is smaller than the individual scores, it will be more likely pointing downwards, right? And then the other way around, if the x, if you're subtracting the mean of x from an x, same concept applies. So the direction of a correlation coefficient comes from the numerator. That gives you the direction. And it gives you a taste for the deviation from the respective mean. So it gives you a direction in terms of the slope, and it gives a direction in terms of whether it's positive or negative. When you look at the numerator, this is basically focused on the sum of squares. So the sum of squares of x and the sum of squares of y. So remember how to calculate the sum of squares. You calculate the individual differences, deviations. You're squaring all these deviations, and you're summing all these squared deviations up. This sum, you're basically multiplying with the sum of squares x multiplied by sum of squares y. You square root it, and you have your denominator. And this will always be positive because you're squaring it. So that's where the sign is not coming from. So the sign is really coming only from the numerator. Now we're going to do this example. You'll see what I mean. Okay, 6 steps of hypothesis testing. Same concept as always. We're identifying population, distribution, and assumptions. We state the null and the research hypothesis. We determine the characteristic of the comparison distribution. We determine critical values and cutoffs. Calculate the test statistic, as we will learn in a second. And we make a decision. Same concept. And this is the example we're going to look at today. We have the data of 10 students, a random sample, that basically had a varying number of absences from class, and we have their corresponding exam grades on a scale from 0 to 100. Okay, you have a spreadsheet on your module on Canvas that basically shows you exactly these data. So just like known, so what is the dependent variable? That's simple, right? That's the exam grade. Or maybe somebody gets so frustrated about class because the exam grade wasn't that good that he or she decides not to come to class anymore. That's a different conversation, please. But basically, you would assume the dependent variable to be exam grades and the independent variable to be absences. So you start off with a scatter plot, which we know already how to do. So you select absences and exam grade. You go and insert. Actually, let me save this first. So you select both variables. You go again on insert. You find scatter plot. We know already what it is. And you just plot the graph. So that's simple, right? So we know already how to do that. And this is the association we have, exam grade. We can make this a little bit more aesthetic as a function of absences. Then we want to do for chart elements, we do axis titles, primary horizontal. That's now absences as a count. With the chart element vertically, we do exam grade as a percentage. And that is our scatter plot. So which direction is it pointing? It's pointing downwards. So that means your exam grades get worse if you have more absences. I think that's a conservative estimation here. A conservative statement seems to be correct. So now first we need to kind of characterize our population. We do that by quantifying a mean average. Average is B2 to B11. So in average, students had 3.4 absences, and we're now quantifying the exam grade. In average, students had exam grades at 76%. So that's the mean. We can do a standard deviation, STDEF is now B2 to B11. 2.5, and then we do exam grades. So there's quite some standard deviation around that 76 mean estimate. It's 76 plus minus 16. So now first we want to do deviations. We're calculating first the deviations. Okay, so this is x minus mx. So x minus mx is easily calculated as this minus this, but we need to lock it in with a dollar sign because the m doesn't change. So that's our difference. We can do this now for all our estimates. Then we do a second one, we do y minus my, which is now basically exam grade minus our mean exam grade. Locking this in gets us these differences. So that's basically the first step that we needed. So now we want to calculate next. We want to first calculate the numerator. For that, we need to calculate that product, which is x minus mx multiplied by y minus my. So now this is just multiplying these two. That gets us basically these products. And now summing this up. So that's our numerator. Simple, right? So that's the numerator. We're calculating first the deviations of each individual levels of x minus the mean of x. We're calculating the deviation of each individual y minus the mean of y. And we're then forming the product for each of these individual entries, and we're summing that product up. So this is now our numerator. Simple. So now we need our squared deviations, and this is now x minus mx squared. Next, y minus my squared. So this is basically this squared, and this is this squared. Oops, a bit too much. So now we also know that we need to calculate now our sum of square x, sum of square y, which is now the sum of these, the sum of these. Yes.
What is G?
What is that?
What's that x minus mx?
That's the deviation.
Oh,
That's just nothing else but this.
the GM,
The GM what?
the column.
That's x minus mx, that's this squared. So that's a square deviation. You remember how we did for the standard deviation? We did deviations, then we're squaring it, becomes a square deviation, and then summing the square deviations up becomes the sum of squares. Same thing we're doing here. Sure. Okay, so now the denominator is now the square root of this multiplied by this. So that's our denominator. So now our r is now in essence nothing else but this. What was it? So all we need to do is to calculate this. So that's the sum of all our deviations multiplying each other. So that's the sum of the product divided by the square root of the sum of squares product. So our r is now numerator divided by denominator. So the resultant r is minus 0.85. And that's all there is. That's correlation right there. Then obviously we also need to have a null hypothesis. So HO, what is the null hypothesis? There's no correlation. And that's the next $1 million question. If there's no correlation, what does that mean? What would the R look like? What would the R be if you have no correlation? Is what?
Zero.
Yeah, it's 0. Exactly. So if the R is 0, that's perfectly no correlation. If you think of that line now, the line of best fit, what would the line look like if the R is 0? Yeah. Bingo. It's flat. So we're testing basically against the null hypothesis that this is an R of 0 and an absolutely flat line. Because logically it has to be flat, because you're basically calculating a dependent variable versus an independent variable. So this is our null hypothesis, R equals 0. So the HA is then, there's a correlation. R is greater or R is smaller than 0. Okay, now that's not nice. R is unequal to 7. Okay, so this is our R, and this is basically now getting us to the next conversation. So we have now, this all follows again the T distribution. If you have your R calculated, you can utilize your R to calculate your actual p-value. And that p-value is basically calculated with this formula. So basically there's a relationship between R and R squared, where R squared, we remember from the eta squared and ANOVA, is basically what part of the overall variability is determined by the between groups variability. You remember that? So it's basically between groups variability divided by the total variability in this group. So it's variance between groups, between variance between groups, and variance within groups. So we're getting to that was the coefficient of determination was regression on Wednesday. So if we're calculating now this T, that's basically R multiplied by square root n minus 2. So n is 10 minus 2. That's the degrees of freedom. Also, don't forget degrees of freedom also in so since it's this also to be determined here, since it's 10 individuals, and you need to take into account two groupings, two variables, you calculate the degrees of freedom as the sample size minus 2. Degrees of freedom divided by 1 minus R squared gets us now a T of minus 4.58. So we know from previous classes that T for a degrees of freedom of 8, where the critical value is 2.31 for a two-sided test, because it distributes in both sides, is 2.31. That means 4.58 is larger than the critical value. Therefore, we're rejecting the null hypothesis and saying there is a significant correlation. So that's how you determine that with this formula. So this is R and this is T. Considerably simple, right? So we did our scatter plot. We know already in which direction this is shaping. We're calculating now individual deviations. We are multiplying these individual deviations for m and x. We're calculating the sum of these multiplied deviations, getting to a numerator of minus 304. Calculating then the squared deviations based on these deviations we calculated before. We're summing them up and then quantifying the numerator as the square root of the product of these two sum of squares. Then we just have to calculate that difference. Well, basically, we have quantified our R. Then we go to test for this null hypothesis. We're basically calculating our T. The T is calculated as R multiplied by square root degrees of freedom divided by 1 minus R. So it's the correlation coefficient multiplied by the square root of the degrees of freedom divided by the unaccounted amount of variability. So it's, if you have an R squared, you're quantifying the amount of variability that is explained for by your calculation. So you're basically quantifying the unaccounted or unpredicted variability. And you're dividing the degrees of freedom by that. So that gets you a T for a two-sided test. Any questions on these calculations? So that's our R. That's this calculation. So it's the sum of the products of the deviations for each variable divided by the square root of the products of the sums of squares for each variable. This calculation of the built-in standardization procedure, that's a fancy term, means nothing else that we're basically quantifying a standardized kind of estimate of that direction by basically taking these products and dividing it by our product of the sum of squares. Thereby, we're standardizing the direction in which this is pointing. And it also takes into account the sample size because it calculates the sum of squares. And you're basically quantifying the variability in the numerator by calculating your deviations. So that's how you standardize this in a way. But keep in mind that there's a built-in standardization procedure in the formula. This will be important because we're dealing with standardized coefficients on Wednesday. And now we're coming to that what I discussed before. So you have now unknown invisible third variables, which are basically having weight in the prediction of one particular dependent variable. So it's very seldom in biological research and physiological research, it's very seldom that only one factor determines a dependent variable. That means there are always several parameters or several variables that basically lead to quantifying one dependent variable. So that means that you need to understand what variables determine a dependent variable. So if you have all three variables measured and they all three are scale variables, so basically the correlation coefficient gives you an idea of each individual association. So you can do A with B, A with C, and B with C. So you get all these correlations, and that way you can basically attribute the associations to each respective pathway. And this is what I mapped out with like this directed acyclic graph. That's basically a so-called Venn diagram, where you're quantifying the respective overlaps between these circles. So if you play weekly hours of tennis, and this associates with the longevity in years, and the weekly hours of tennis associate with years of education, and the years of education also associates with longevity in years, these are all known associations. So it's like the more education you have, the longer you live usually. The more education you have, the more likely you could be playing tennis, or the other way around. So maybe somebody who plays more tennis is more likely to have had more education. So there are various possible correlations embedded in that. But basically, the dependent variable is here at these intersections. And there are a certain explanatory power coming from each of these variables. And that's partially correlation, essentially. It's basically you're trying to predict variability in your data, and you're trying to predict adverse variables that are partly associated with this and thereby could have a causal relationship. We'll talk about this more on Wednesday when we talk about multivariable regression. Any questions on that? It's just a concept a little harder to grasp, I understand that, but it's basically coming back to the ice cream consumptions. So you have the temperature, then you have, I don't know, preferences of students, then you have, is there an ice cream truck right in front of the school? So there are many factors that build up the ice cream consumptions per se. And all of these can be quantified, and the weight of these can in can be attributed to each of these factors. Where this particularly is important is in psychometrics. So psychometrics is essentially a science by its own right. So it's the development of tests and measures. And tests and measures are getting more and more used. In psychology, obviously, they've been a very typical tool. So you have questionnaires, you have surveys, a very common thing. It finds its way now slowly into the realm of clinical medicine, which is a good thing. Because essentially you have standardized questionnaires that you're handing your patient. And there's some intriguing thoughts why this is good. So as a healthcare provider, you want to understand how does your patient really feel. So it's a subjective assessment of that patient's quality of life, perception of health, health condition, pain, depression, quality of life with kidney disease. There are various questionnaires out there that basically allow you to quantify how does that patient actually feel. And that becomes now in Medicare reimbursement, it's like a standard measure that they want healthcare providers to do quality of life service. It's a very common thing nowadays. So psychometrics is really something that has very much moved in the forefront for a very good reason, because it allows to understand the patient, but it also allows the patient to reflect on his or her own well-being. So that's a side effect essentially of having them fill out questionnaires. But these questionnaires, so they're very complex questionnaires. So like there's a whole body of literature and science on developing these psychometric assessments. And so they are long, so they have questions that are validated, and it's clear that they're really reflecting what that patient wants to actually say, of how the patient actually feels. And they need to be also translated into various languages. So if it's validated in English, that doesn't mean that, I don't know, somebody in Austria or somebody in China would answer that question the same way, right? It's like, so you need to validate them in different languages, different cultural settings, different countries, different healthcare patterns, you name it. So various things need to be taken into account. And this is the work of psychometricians. So these are experts on psychometric assessments. And for them, correlation is basically their daily bread. So they use this to for the development of these measures, and they test, and we have talked about this already, they're testing for reliability and validity. So just as a recap, when we talked about this, validity is what does this tool measure, and does it really measure what it's meant to measure? Is the assessment accurate? If somebody gives you a quality of life survey, is that quality of life assessment survey really reflecting what the quality of life of the patient is? Reliability is if I give that patient that survey today, and I give it again to the same patient in half a year, everything else being equal, is that gonna be a reliable measure? Reliable measures are consistent. And this is being tested. This reliability is basically measured within the individual. So you have, whenever the test is taken, it's consistent outcomes. So you have consistent assessments, and this is done in a so-called retest reliability assessment. Secondly, you have a so-called split half reliability. And this basically means you have a survey that contains 200 questions. You want to know whether all the questions of the survey actually give you a really reliable estimate of whatever you mean to quantify. You do that with a so-called split half reliability. So you split this into odd numbers and even numbered items. And then you take the odd numbers and you correlate them with the even numbers, and you say there's a correlation. Ta-da! That means it's a reliable measure. That's one way to go about it. A second way to test for reliability is the so-called internal consistency, which is quantified as alpha, the coefficient alpha, also called Cronbach's alpha. So Cronbach was the statistician who came up with this. So basically, it is used as a test or measures reliability. It's basically done by quantifying the average of split half correlations. So you have 100 assessments in 100 different participants, students, patients, whatsoever. You calculate that split half reliability, and you're quantifying the split half correlations. For each individual, you get an average, odd, even, and then you take all this odd, even, odd, even, odd, even, and you build a correlation. That's your Cronbach's alpha. Can consequently range from 0 to 1, not -1, just 0 to 1, because it needs to be a positive correlation. If this is not a positive correlation, then your questionnaire is not too good. And so it needs to be a positive correlation between 0 and 1. As a cutoff of a reliable measure, you would assume it to be, differs a bit in the literature, 0.75, I think is the most commonly accepted threshold. Not a quiz question, but just for FYI. Yeah, so valid measures are basically, these are measures that measure what they're really supposed to be measuring. How would you know that? Well, not easily, bless you. Not easily, but you basically do it by taking the measures you have from your questionnaire and you associate it with other variables that you quantify in some other shape or form. And you basically, you're associating these other variables with the assessments from the questionnaire. Let's say you're doing a quality of life questionnaire, or you do a general health questionnaire, and you get a certain measure of that quality of life or that general health perception, and you associate it with the number of hospitalizations the patient had over the course of the last 2 years, and there's an association, then you know, my questionnaire is maybe not that terrible. On the other hand, if it shows you a really good general health perception and the patient was in the hospital 10 times over the last 6 months, then you know your questionnaire is maybe a little off. So that's the concept of this. Yeah, and lastly, Nolan and Heinz just want to make a point that validity and personality quizzes are basically useless. And I tend to wholeheartedly agree. So all these, I don't know, whatever magazine you may be reading, whatever quizzes you fill out, they're more for an entertainment purpose than anything whatsoever. So they have never been tested in terms of psychometrics. So they're just basically something that was made up for pure recreational entertainment purposes. Good. Okay. Any questions on any of this? Psychometrics is important. I highly flag this. Quite an important topic. If no questions, then we can go back to our spreadsheet. And I want to show you a last thing. It's a little bit going, moving towards regression. I just want to quickly talk about the concept of this. So we know when we click on the graph and we're going to insert, oh no, wrong. If we click on the graph and we go on format, no, we're going chart design, finally. And we go on add chart element and we add a so-called trend line. If we do linear, we get a linear line. So now you may ask yourself, okay, so now we have this line. How can we characterize this line? And there are 2 factors for this line that are really important in this context. One is, where does the line start? And that we will learn to call the so-called intercept. So this is the point where that line basically hits x equals 0. And the second thing you want to know about that line is, so it continues into infinity. So it's basically, it's an infinite line in both directions. What you also want to know is like, how much is this decreasing over time? And how can you quantify that? It's considerably simpler because the only thing you really need to know is the so-called slope. And the definition of such a slope is basically if I increase on my x 1 unit, how much does my y decrease? That gives you a slope. So basically, if I go from 0 to 1, and that's how easy it is, you basically just need those 2 points. You need 0 and a 1. If I go from here to here, how much does that line decrease in y? So the slope, so the unit of the slope is basically the unit of your y, because that's the decrease per 1 unit decrease in your x. So for the context of exam grades, it's basically percentage of decline per absence. So if I were to quantify now this line, and let's say this is here, let's say here at x equals 0, what is that? I would say that's like, okay, let's maybe take 1. Let's take x equals 0 is, let's say 95%. At x equals 1, this is only 90. At x equals 2, this is already down at like 84. Would you agree? Something like that. Let's do it 85. Makes a prettier number. So now, those of you that remember, you're in high school, you should have learned about that. A line equation is shown as y equals, and this is where our experience may differ because I learned it as y equals k multiplied by x plus d. I think in the US it's y equals a multiplied by x plus b. I think, right?
I know it's
M?
Oh, and equals 5 plus MX. Yeah. Yeah.
Which was M, the slope or the intercept?
A.
The A is M? M. What does M stand for? All right, good.
I wish I don't remember.
All right, well, same concept, same concept. So basically your B is that point where it starts. Your M is that difference, that y that it decreases from one to another. And your M is equally calculated as, and you can do this quite simply. It's basically y2 minus y1 divided by x2 minus x1. What does that mean? It's basically the difference from this minus this divided by this minus this. That gets you the slope. So if we're calculating this through now, we're doing m, and this is now this is now y2 is now what did we say, 85 minus 90 divided by 2 minus 1 gives you now a slope of somewhere around 5, right? So m is 5. And the unit of that is percentage per absence, right? So, and that's simple. And now we can confirm this. We're basically clicking again on the trend line. And now we say display equation on chart and display an R² value on chart. So now we have y equals minus 5.3. Oh, course, it's minus. Oops. Of course, 85 minus 90 is minus 5, correct. Okay, so we have minus 5.4 plus 94.3. So 94.3 is where this started. So these estimates that I put forward here were inaccurate, but you get the concept, right? So this is the excellent way to show you this line equation, and we've just calculated it. So this is a line equation. This is so-called regression equation. That's nothing else but a regression equation is. So now we have the R squared, and we will get to that on Wednesday. The R squared at the end of the day is nothing else but R squared in the simplest example. In the simplest example, this is nothing else but R squared. And this is where the 0.72 are coming from. So why do we have to do that? So the R gives us an idea about the strength of the association and the direction. The R squared basically goes on the next level. The R squared basically is our so-called coefficient of determination. And with regression, we're going to discuss this on Wednesday. This is basically the amount of variability in our data that is explained for by the regression equation. And we will get to that on Wednesday. So this is beyond. But basically, just keep in mind, R squaring the R is R squared. Good. Any questions? If not, then have a nice evening. See you on Wednesday. Study for the quiz. Hi. I do not, but now I do.
Oh, now you love
I know. Thank you.
Thank you.
Thank
Thank you so much.
Thank you. You too.
Night.
Good night. All of us.
Thank you so much.
Thank you. Bye-bye. You too.
I don't know.